That's right. We cannot have any water added to PCC because PCC will react with water and basically quench itself, which means that it will not proceed to get rid, or not get rid of the alcohol, but to convert the alcohol. So what's another condition we need to have for PCC to work? We need something very, very specific. We need a hydroxyl, right? And in addition to the hydroxyl, we also need to have an additional proton that's sitting on that carbon the alcohol is attached to. So short, sweet, and simple, we need to have two hydrogens. We need to have one that's sitting on the alcohol, and we need one sitting on that opposite end carbon, because PCC, I will not show you the arrow pushing for this because it is a nightmare that you will never forget. All you have to know is that it's going to turn our alcohol into a carbon double bonded oxygen. And in order for it to do so, it has to be able to remove the proton off of the alcohol to make it an oxygen minus. And then it has to remove a hydrogen with the electrons from this carbon in order to drop the electrons down. That way that carbon can accept those electrons. All right, PCC, very, very straightforward. And that's going to be where our first step begins. We're going to create a ketone for our Grignard to attack. So, if I draw a little bunch of squiggles here, that's going to be the beginning of our second step, is introducing PCC to this molecule so we can get a ketone out of it. Because again, we got the Grignard, but we need something for it to attack in order for it to actually, do what we want it to do. So there we go, we got our molecule. Let me just scooch this up a little bit so you guys can see it. Right, so we got this guy. And right, we're just going to toss some PCC into this. And now, it's assumed there's no water in here, but if you want to, you can write below the arrow, no H2O in parentheses. Again, we wouldn't assume there's water thrown in there unless we add it to it. But right, we can't have water with PCC because again, it'll react with the water because PCC needs 2 protons, right? Water's got 2 protons. So PCC will basically just smother the water molecule instead of the alcohol. And then our reaction does nothing, and then we're sad. But basically all PCC is going to do here is going to create that, that sweet ketone that we're all, after, right? And the other molecules remain untouched. The methyl up top, same plane. Our nice little methyl ethyl down there, he stays the same too. But now we have a carbon double bonded oxygen there. So now what do you guys think the next step's going to be? Alright, so we got a ketone. We made a Grignard in the previous step, so what's our next stage here?
Elimination.
So it won't be the elimination. We actually haven't added the Grignard to this yet. So our next step is going to be the addition of the Grignard to this molecule. We made the ketone for the Grignard in the first place. So I'm going to continue the reaction down here, and it's going to be a 2-step process. I'm going to take away your low-hanging fruit. I'm going to introduce the Grignard right here. Right? We introduce the Grignard, then what's coming in step 2? What do we add to it afterward?
Magnesium.
Yep, some sort of proton donor. More commonly, right, H3O plus and or H2O. But we toss these guys in here, and that is what's going to attach this methyl that we see in our final product. And that's going to be the part we want to get first. Whenever you see a new carbon molecule attached, you want to get that put on there first. Because Grignards have to attack ketones. And if you turn your molecule into a ketone as a final step, you might possibly not be able to add the Grignard on there because you may not be able to turn your molecule into a ketone later on. So you want to turn it into a ketone or aldehyde at the very beginning. Get the Grignards out of the way first. But right, so we attach this guy here, right? We should know the arrow pushing for this by now. But right, this stays the same, this stays the same. And what's attached here?
Methyl.
Alright, we got a methyl here, and what else is there?
OH.
Yep, there is a hydroxyl there. So all we've done now is literally attach a methyl there. We've got the alcohol back again. But But alrighty, so we're almost at our final product. We're almost there. But we still have that double bond we still need to address. So we still need to get this guy, and also somehow this alcohol gets eliminated, so to speak. So what are we going to do next here?
E2. Or E1.
We're going to carry out an elimination reaction. Now, what is a good molecule that we love to use for eliminations?
Sulfuric acid.
H2SO4, sulfuric acid. And now we really want to make sure this guy's going to carry out the elimination pathway. So what is one other thing that we can add to this to make sure elimination is the only thing that happens here?
Heat.
Heat, right. So right below the arrow we can put a little triangle there to represent heat, or we can physically write heat underneath the arrow. But right, we can get rid of the alcohol and create that double bond that we see in our final product using the elimination 1 pathway. So alcohol gets removed, and we replace it with a double bond. Now, how many products should we theoretically get from this? We should get 2. But I'm sure you guys have taken a brief look at the answer key, and you guys see that only one of the 2 possible products are actually drawn. So we get these 2 guys right here, and then the methyl is just attached there at that carbon. We could put the double bond, like I said, we could put it theoretically here or here. So we should get 2 products in the end, but why do we only draw one of them? Yeah, because that's the one we're after. We're after this particular one, so we don't have to actually draw this. We know there's a second product there because we can put that double bond on the other carbon, but that is not the product that we're after. We're after this one. So we have to specifically draw us getting to the product that they're asking for. So we only draw this guy. And now as a quick check, how did this guy lose his plane again? Why is he no longer dashed? Why is he no longer that anymore? That's right. There's no stereocenter there anymore. Once you put that double bond there, that carbon no longer has 4 unique substituents. So we no longer need to indicate that methyl ethyl is dashed anymore. We can represent it as a single bond line. And okay, that's all there is to it. That right there is 32 points right there. That's all there is to it. Like I said, quick recap here. And actually, I didn't label this, but this would technically be step 3 overall, and this would be step 4 overall. So this is literally a 4-step reaction process. So basically each step is worth 8 points. And now to cover some quick common questions about this. So we added a Grignard down here. Did we have to show that we made the Grignard back in step 1? And the answer is yes, because did we start out with a Grignard as one of our 2 starting materials? No. So if we're going to use a Grignard, we have to show how we got it. We have to show how we made it. Any modifications we make to the starting materials have to be shown in steps. Now, could we have drawn this guy first and then over here on the side made the Grignard? Of course. But it's easier to get the Grignard made right from the get-go, so we have that kind of on the side and we don't forget to draw it in later, because as a force of habit, we're like, ooh, we use PCC, then we know this could be a Grignard, but then students will forget to draw the actual creation of the Grignard, and they lose basically 1/4 of the points there because they don't draw how the Grignard was made. But alrighty. And another question that is commonly brought up on this is, couldn't we technically also use a strong base down here to favor the E2 mechanism to make sure that we get that same product? And the answer is yes. You could use a strong base down here and do E2 on this thing, and you'll still get the final answer up here. But you guys have all been conditioned to learn sulfuric acid as the main producer of elimination products. So instead of making you guys memorize what's a strong versus weak base, and in case you guys are iffy about those, sulfuric acid is just about a guaranteed E1. So if you need to get elimination done, try to see if you can use sulfuric acid on it. Unless it's on a primary carbon, of course, then you have no choice but to use the E2 pathway. But for secondary and tertiary, you can throw sulfuric acid in there and you'll get a nice E1 product. But okay, so with all those steps laid out, that's a lot of material there. Are there any questions you guys have on this? Hmm?
You know it was PCC because of alcohol, right? That's how you use PCC for the first step?
Yep, good point there. So, because an alcohol was present here, is that how I knew to use PCC on this? Yes, that is the big thing that gives away PCC is going to be involved here at some point, because you got a methyl that mysteriously attached there at that carbon. So that means at some point this had to have had a carbon double bonded oxygen on it. And what's one thing that we know that can make those out of alcohols? PCC. So there's a bunch of little hints there that kind of tell you, okay, I need to attach this carbon on here somehow. And we have a bromine here. Like I said, the bromine's what tells you need a Grignard in the first place, like the very beginning of this problem. Having a bromine sitting there just on that methyl and knowing a methyl attached somewhere along the way means you made a Grignard somewhere. Mm-hmm.
Would you still use PCC if you had an aldehyde instead of the ketone?
Ah, good question there. So would we still use PCC if we were trying to produce a aldehyde as opposed to a ketone? The answer is yes. PCC just makes the C double bond O piece. So if we're comparing the generic formulas for a ketone versus an aldehyde, PCC makes this part. Now, what is around that carbon double bond oxygen can vary, but you would use PCC to make an aldehyde or a ketone. It can do both. It technically just makes carbonyls if you're going to be really technical with it. PCC just makes carbonyls, which carbonyl is the C double bond O functional group. Now, what it has around it doesn't really matter. If you have a C double bond O, you can then introduce a Grignard later on that will greatly attack it. All right. Any other questions on this one? Like I said, this is a pretty hefty question. Good question. So, here I have all of the reaction steps numbered. Do we have to number the steps in our final answer? And the answer is no. You just have to make sure you have all the reactions laid out and the arrows are all pointing in the correct direction. So that's all you're going to need for this is just the arrows. That's all you need. You don't even need to show the arrow pushing for it. You just need to show we're going from here to here, here to here, and these are the reagents we use. Mm-hmm.
Can you explain how the stereo matrix changed from dashed to like a straight line? The bottom?
So the question here. So how do we go from having a dashed configuration in here to having just a simple stick over here in our final product? So when we collect this alcohol off of here and we create that double bond on this particular side, putting the double bond right here is going to eliminate this stereocenter. So we're no longer going to have a stereocenter at that carbon, which means that we no longer can say this guy is dashed or wedged anymore. This guy is now just going to be just a simple bond line because we only put dashes and wedges on stereocenters. And if we don't have a stereocenter there anymore, then we have to use a simple bond line. Same thing with our nice little methyl out over here. We don't know what plane he's on, but it doesn't really matter because we don't have a stereocenter there anymore.
Could you add the PCC and the magnesium at the same time?
Good question there. So could we theoretically have PCC introduced here, but then also introduce magnesium at the same time with the methyl bromide? The answer there is technically yes. You could have both of these two be your first step, so to speak. Now, you can't really toss magnesium in here with this guy because it won't actually do anything, and vice versa, PCC won't do anything with this. But you could list them both out like on the same level. These could both kind of be your step one, so to speak. There isn't really an order. You just have to make sure that you've got a Grignard built by the time you add PCC to this molecule over here. And that's pretty much all that matters there, is you show how to get this guy right here. Any other questions on this one? Good question so far. The $1 million question. How could he change this on the midterm? Let's see if I can think. Instead, let's say instead of this, he wanted you to show how to get this. This is just me just pulling stuff, just out of the darkness. Yep, pulling it out of cyberspace.